So we're still in 7.4. So 7.4 is about searching algorithms. And again, we can imagine that we have values stored in an array. And your array, we're going to keep track of an array as a length, which I've been using n to indicate the length. This comes from linear algebra, where n is the number of rows in a list, or in a matrix. You have m columns and n rows or something like that, or n-dimensional vectors. It's less to write than length, and so I'm going to stick with using n. And it's kind of a convention that n is the length of things. And we're going to have an array of values. So in your book, it's got an example with 11 strings, and they're called items. So items is an array, and it's an array of strings. And I think I've talked before about how you might represent an array of strings. But for now, just imagine that it's possible. And items this is kind of important, it's sorted. And the reason that that's important is because we're going to talk about an algorithm called binary search. And what it does is it exploits the fact that it's sorted to come up with a much faster way to search through items. For instance, let's imagine, let me just write out what we've got. We've got ant, cat, chicken, cow, deer, dog, fish, goat, and so this is alphabetical order, and it might be fun to think about how you could write an algorithm to determine whether one string is less than or greater than the other in alphabetical order. What is the algorithm that we use to compare? So let's make sure that this is right. This should be at index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the indexes of each string, and there are 11 strings. I skip over 10 of them to get the 11th one. Right, so there's a total of 11 strings. And so how could we do better than a linear search? So if we wanted to look for salamander, well, salamander isn't ant, it's not cat, chicken, cow, deer, dog, fish, goat, horse, rat. And then I have to look at snake, and I know that salamander comes before snake, so since I've seen snake, I know that salamander isn't in the list, but I'm at the end of the list anyway. So basically, in the worst case, if I do a sequential search on n algorithms, how many operations did I need to do? So how many lines of assembly, or how many instructions of pseudocode would I have had to do? And it's too hard to count every line. So sometimes we just kind of ballpark it and come up with a waving hands on the order of number. It might be good to count the number of comparisons. So here we had to do, we had 11 items, and we had to do about 11 comparisons. So about n. We're going to say that this is an order n algorithm, right? Order n comparisons. If you have n numbers, you have somewhere on the order of n different comparisons you would have to do. Now, is it possible to do much better? And we'll find that it is, because we're going to use something called a binary search. And I wrote a little pointer. Here we go. So here we have a nice little pointer. The sequential search was an algorithm that, oh, my pointer goes the wrong way. Let me just kind of flip it around here. The sequential search was an algorithm that started here, at 0 and slid down in kind of the most naive of ways. And we can do a little bit better than that, because since this is an array, we can jump to arbitrary spots, and we know that it's sorted. And so our goal is going to be to come up with an algorithm that avoids looking at every single item. So in a sorted array, if I was looking for Dalmatian, I don't know, I just came up with something, I would see cow and deer, and I would say, oh, I can skip all of this stuff. Since deer is bigger than what I'm looking for, I know that everything else is also bigger than what I'm looking for, and I can rule out a bunch of the things. However, if you do that with a sequential search, in the worst case, you still have to look at everything, right? And that worst case can be pretty common because maybe all of your words begin with an A, right? So in the worst case, you still have to look at everything. So how can we be a little bit smarter about how we can rule things out? And the idea here is instead of looking at the first item first, we could look in the middle. So maybe I'm looking for Dalmatian, and the very first comparison I do is with dog. And I can see that Dalmatian is less than dog. And because of that, I can safely rule out all of this stuff. In fact, Dalmatian doesn't equal dog, so I can rule out dog as well. And so I know that what I'm looking for has to be up in this top part. And so now I can take that top part and I can look in the middle of the top part. And I compare Dalmatian to chicken. And Dalmatian is bigger than chicken. Since Dalmatian is bigger than chicken, I can rule out anything that is less than chicken. Because if it's less than chicken, it's also less than Dalmatian. In fact, if it wasn't equal to chicken, I can rule out everything above and including chicken. Which means now I pick something close to the middle here. There is nothing in the middle, so I just have to have some rule. I'll round up, or I'll round down to the lower index. So Dalmatian is bigger than cow and not equal to deer. So I can figure out that Dalmatian isn't in here, and in order to determine that, I had to compare it with dog. I think, what did I do? Chicken, cow, and deer. So something like 4 comparisons, right? So with 11 numbers, I had to do 4 comparisons, right? So remember, when we're dealing with small numbers, like around the order of 10, we represented them as 4-digit hexadecimal numbers because you need about 4 bits for numbers that are about this big. Right? So this binary search took 4 checks, and it's no coincidence that the number of probes that you have to do in a binary search is the same of the number of bits that it would take to represent your number. So for instance, a number like 256, 255 takes 8 bits. And if we had a list of 255 elements, instead of being order 255 or order n, we would be more like order 8. So we're going to do a binary search algorithm which works by trying to prune out half the list at every time. And that's going to be about on the order of what we call the log base 2 of n. And when you hear log, think the number of digits. Think number of digits. Actually, log, L-O-G, is the number of digits, and L-G is the number of bits that it takes to represent n. Okay, so this is pretty cool because we can't store arrays in our computer. Remember how much memory our computer has? It had from 0 to the largest address that we could store in our computer was 2 to the 16th power minus 1, right? Which is something like 64K. I think it's actually 65,500 and something. I don't know. Let me find out the actual value, just for completeness. 2 to the 16th minus 1. So the largest value we could represent is 65,535. In order to search through an array that's the biggest array we could possibly fit in our computer, it's going to take us 16 steps, 16 comparisons. Whereas a sequential search would need 65,000, our algorithm only needs 16. Right? So this is substantial. This is it grows so slowly it almost looks like it's constant. Right? Let's look at how this actually works in pseudocode. So again, the idea here is we're always going to try to find a number close to the middle so we can rule out, if we find it, we're done. If we don't find it, we can rule out about half of the array every single time. So I'm going to just throw the pseudocode. This is pseudocode from your book on 219, page 219. So we're looking at page 219. We're going to keep a variable called, so what we're going to do is we're going to have, remember when I was doing the algorithm, I started masking off parts of the array. What we're going to do is we're going to keep track of a couple of special values. So we're going to keep track of the first item, which is the very first item of our array. And you know what? I'm going to do this on the other side. So the first item of the sub-array that we're looking at. So we kind of have a first location, and we're going to also keep track of a last position. So we keep track of first and last. And I wish I hadn't put so many notes over there, so maybe I'll just try to mask them out. So we have first and last. Right. And we're going to move those around as we narrow down the range of where our value can possibly be. All right? And actually, I want to write last like this. I want to be pointing up. So that the first and last can both be pointed at the same thing. So right now, our last is 10, because that's the last item in our array, and our first is 0. And that represents your entire array. So we got that kind of idea. We are going to introduce some pseudocode. So what we do is we set first to 0. It's pointed at the beginning of the array. And then we're going to set last to be n minus 1. So it's pointed at the very last item of the array. It's not 11, it's 10. All right? And now we're going to set found to false, just like in a sequential search. Our condition is going to be similar while we want a condition that says the list, the sublist, this region of the list, this sublist between first and last is empty. And we'll know that first and last is empty if last, so this would represent, if I could do it, this represents a list of one element, right? First and last are both index 9. That means that we've got one element wrapped. Okay, so this would be first is 9 and last is 9. So when first equals last, we still have a list. It has one element in it. In order to be empty, we would have, these things would have to cross. So if last was 8 and first was 9, then there's nothing that could possibly be in there. That represents an empty list. I know it's a little bit weird, but that's going to be the condition for us to have an empty list. So our condition that says while we haven't gotten down to an empty list, meaning we've gotten rid of every element, we've pruned every element out, that condition is going to be while the first is less than or equal to the last element. Okay, when they're equal, you have one item, but when last is less than first, there's nothing that can fit in that range. Okay, and so we have two conditions, and we haven't found it. So we're going to, instead of saying found equals false, we're going to say not found. It's the same thing, right? And we haven't found it. Okay. What do? We're going to create a new variable called middle. And that's going to be pointing somewhere in between first and last. You know, this camera's killing me. So we're going to have a new variable called middle, and it's going to be somewhere in between first and last. Right? Okay. So set middle. And we want it to be halfway in between. And so I think we've already talked about if I have two numbers and I want a number halfway in between them, then I add them together and divide by 2. And that gets you a number in halfway in between first and last. And these are supposed to be integers. And so suppose I wanted to add 1 plus 2 and divide by 2, then I would get 3 over 2, which would be 1.5. We're always going to round down. And your pseudocode doesn't show you this, but we're going to be looking at the floor. So this little symbol, it's vertical lines, and rounding down, you put a little bar at the bottom. So this is the floor operation, and it is the greatest integer, which is less than or equal to that expression. So if this comes to be a 1.5, what we're going to get is a 1. Basically, we're chopping off, for positive numbers, we're chopping off after the decimal point. For negative numbers, it works differently, but that's the definition of it. So we're going to set middle to that. In this case, we have first is 0, and last is 10. So 10 over 2 would be 5. And so there we go. And then if so the thing that we're searching for, we're going to call that thing item. So whatever we're searching for, we're going to call that item. So if item is equal to the data, so this array is called data, at index middle. So if the thing that we're looking for is the thing in the middle of the array, then we're done. So we set found to true, right? That's it, we're done. Otherwise, we need to shrink the range of what we're looking for. We need to shrink first and last in a little bit. So else, here we got a nested structure. So this whole thing is important, goes in the else. So this isn't else if. This is else with a nested if. And maybe you should try to think about what the difference is. If item is less than the data at the middle, meaning whatever I'm looking for must have been up in this region somewhere, then I'm going to change last. And I'm going to set it to, now you'd think I could set last to be middle, but I already know that middle is not what I'm looking for. So what I'm going to do is I'm going to set last to be middle minus 1. Right? So last goes up just 1, because I know that it's not dog anymore. So now I know whatever I'm looking for has to be an index 0, 1, 2, 3, or 4. It can't be at index 5. Right? So I'm going to set last to middle minus 1. Right? The middle is still pointing up here at 5. Right? And else, so this would be the other situation. The item that I'm looking for was greater or equal to the data at the middle. But it couldn't possibly have been data at middle, because if it was, I would have gone down this branch. So since I'm down in this branch, because I'm in this branch of the loop, I know that this previous condition is false. So I know that this item is not what I'm looking for. And since the thing I'm looking for is not less than that, it must be greater than that. So the thing that I'm looking for must be in index 6, 7, 8, 9, or 10. So what I'm going to do is I'm going to set first to be at middle plus 1. So first is going to be set to 6 here. All right. So that would mean I've reduced the search range to here. Okay. Once I'm done with that, I go back up to this while loop, and I repeat the process inside of this range. So I set middle to be in between, and the whole process continues. I'm going to stop this video right here. This is binary search. I want to trace the execution of this, but I feel like it's a little bit too awkward to do on this little piece of paper. So I'm going to try to find a better way to trace the execution of this.